Hi friends, in our last session we have discussed gas laws, that is Boyle's law, Charles law and Gay-Lussac's law. In today's session we will be discussing combined gas law, even it's called a combined gas equation, and from that we will derive characteristic gas equation and ideal gas equation. This is Faizan Kagvi and I welcome you all to our lecture series of Basic Mechanical Engineering. So let's begin with our topic, that is combined gas law. Now the question comes that why we need to combine gas equations, that is gas laws. Why we need to form combined gas law? So the main reason is that in actual practice we have real gases such as nitrogen, hydrogen, oxygen, air, which can obey either of these laws, either Boyle's law, either Charles law or either Gay-Lussac's law, that also under a specific conditions of pressure and temperature, not under all conditions of pressure and temperature. Okay, and we have other gases which are not real gases. So in that case, on that gases we cannot apply this law. So for that we need to determine an intermediate condition which can be obtained only by combining these gas laws. As we know that we need to find out various parameters of gases, such as what is the mass of a gas, then pressure of a gas is how much, then temperature is how much, then volume is how much. So how we can determine these parameters? So this can only be done if we combine all the gas laws. Okay, that is Boyle's law, Charles law. Now when we combine Boyle's and Charles law, then automatically Gay-Lussac's law will be covered, as a volume parameter will be covered in that. Okay, so the main reason to do this is to determine an intermediate condition which will be applicable on all the types of gases. So this is the reason why we need to combine gas laws. So this is basically a derivation of 7 marker which will be asked in your GTU examination. So as you can see on your screen, I have shown a pressure versus volume diagram. Now you need to consider a gas present in a piston cylinder arrangement and it performs two processes. Let's say I have considered that the gas is first going to follow Charles law, that is going to perform a process according to Charles law from state 1 to state 2, and after that the same gas is going to perform the process Boyle's law from state 2 to state 3, as you can see on your screen, represented by a horizontal line from state 1 to state 2 representing a Charles law, that is pressure P1 is equal to P2. From state 2 to state 3 we know that the isothermal process or Boyle's law is represented by this hyperbolic curve. So where temperature T2 will be equal to temperature T3. Okay, so remember that we are going to combine these two laws. Okay, so first of all we are going to apply Charles law on our process from state 1 to state 2. So what will be the equation according to Charles law? We know that V1 by T1 is equal to V2 by T2. Now in this equation we can say that as we need to combine, then we are going to focus on our another process, that is Boyle's law. So from Boyle's law we get a result that T2 is equal to T3, right? So we can substitute T3 in place of T2 in our equation of Charles law. So I have written the equation, final equation, V1 by T1 is equal to V2 by T3. Let's say this is our equation number 1. Okay, now next we need to apply Boyle's law on our process from state 2 to state 3. So let's see that. Now we know what is Boyle's law. So according to Boyle's law the equation is P1 V1 is equal to P2 V2, right, which we have seen in our last session. So now applying Boyle's law on our process from state 2 to state 3, so the equation is going to become P2 V2 is equal to P3 V3. But since as we can see that from our process from state 1 to state 2, pressure P1 is equal to P2 and we need to combine both the equation. So again in our Boyle's law equation we can substitute P1 in place of P2. So the equation after substituting is going to become P1 V2 is equal to P3 V3. Now making V2 as a subject, which is V2 is equal to P3 V3 by P1. Let's say this is our equation number 2. Now this equation we are going to substitute in our equation number 1, as we need to combine equation of process 1 and equation of process 2 in order to obtain a combined gas equation, right? So after substituting the equation 2 in 1, we will get P1 V1 by T1 is equal to P3 V3 by T3. This is obtained after arranging the terms. So from this equation we can conclude that P into V upon T is equal to some constant capital C. Now this equation which we have obtained is called a combined gas equation. But this equation cannot be applied directly to any type of a gas. Why? Because this is not a generic equation. This is not a generalized equation. Why? Because the value of constant C will be different for each and every type of a gas. Okay, so we are going to consider two cases. We need to determine that on which parameter this constant C can depend. So there are two most important parameters which will be different for a different gases. Okay, so the first parameter on which a constant C can depend is a mass of a gas. Okay, and a second parameter is molecular weight of a gas. So as we know that molecular weight of each and every gas will be different. So if it is different, so the value of C will also be different for different gases. So we are going to consider two cases. Let's consider the first case. So case 1 is a one in which we are going to consider same gas having different masses. Okay, same gas means a gas having a same molecular weight, but a variable parameter will be a mass. So we know that a constant C will depend on a one which is a variable. Okay, so in this case 1, we would say C is going to depend on mass of a gas. Why? Because it is variable. Now, so I have mentioned this equation PV by T proportional to M. Okay, I have not written equal to M. Equal to M means C is equal to M, which is not that. The case is C depends on M. So whenever something depends on something, so we need to represent it by proportionality. Okay, so I have written over here PV by T is proportional to M. Now let's say removing a proportionality constant by some another constant, let's say that constant is capital R. So we are going to get an equation PV is equal to MRT. This equation which we have obtained is named as a characteristic gas equation, and the constant capital R is called characteristic gas constant, whose unit will be kilojoule per kg Kelvin. Now we can even determine the unit of R by simple technique that we know R is equal to, making R as a subject, so R will be equal to PV upon M into T. Now what will be the unit of PV? So we can say that PV is basically a work done. We know work done formula, P into dV, right? So what is the unit of work done? So we would say joule, or we can say kilojoule, right? So PV unit is kilojoule upon mass. So mass unit is what? Kg, and temperature unit is Kelvin. So from that we can write the characteristic gas equation unit capital R is kilojoule per kg Kelvin. Okay, so this is, we have seen just case number 1 in which we have considered that a constant C is going to depend on our mass of a gas. Now the second parameter is remaining, that is molecular weight. So in considering that case, case number 2, in that case we are going to see that is same mass but different gas. So in this case, different gas means different molecular weight, which means one of the gas is, for example, oxygen gas, another gas is nitrogen gas, but both the gas has the same mass. Okay, so in this case too, what is a variable? So we would say the variable is a molecular weight, and in this case C, that is constant, is going to depend on molecular weight of a gas. Now for considering this case, there is an hypothesis called Avogadro's hypothesis. This you have already studied in your 11th and 12th standard. So what Avogadro has told? He told that equal volume of all the gases, if they are at same temperature and pressure, then they will occupy same number of molecules. So I have shown an example over here that I have shown two containers. Let's say first container has a nitrogen gas, second container has a oxygen gas. both the containers, the gas has the same pressure, same volume and same temperature as told by Avogadro's. And let's say N is a number of molecules of a nitrogen gas and NO is a number of molecules of a oxygen gas. So by using kinetic theory of gases, which you have already seen in your 11 and 12 standard, we have obtained an equation in which we get that Nn, that is number of molecules of nitrogen gas, is equal to number of molecules of oxygen gas, provided if both the gases has the same pressure, same volume and same temperature. This is what is told by Avogadro's. And from this hypothesis we can even conclude, he also concluded that V will be proportional to N, where V is the volume of a gas is directly proportional to the number of molecules of a gas. This can be also easily understood by taking an example of a balloon. If we fill air inside a balloon, so what we are actually doing? So we would say we are increasing the volume of a balloon. If we are increasing the volume of a balloon, then directly we can say that we are actually increasing the atoms or molecules in a balloon, right? Higher is the amount or quantity of air present, higher will be the number of molecules. So whatever change or whatever increment in a volume takes place is directly proportional to the number of molecules. If volume increases, then number of molecules are also going to increase. So from this we can conclude V is proportional to N. So let's see that what does mole represents. So mole, denoted by small m, represents number of atoms or a number of particles presenting 12 gram of carbon. Remember, 12 gram of carbon. And it has been found by Avogadro's that it is equal to 6.023 into 10 raised to 23 atoms or particles, which is equal to 1 mole. Okay, so since it is for a 12 gram carbon, so 1 mole is also represented as a 1 gram mole. Okay, so 1 gram mole can be written is equal to 6.023 into 10 raised to 23 atoms. So this is for a 1 gram. So what will be for 1 kg mole? So we would say that for 1 kg mole, it will be equal to 6.023 into 10 raised to 26 atoms. Okay, so now let's derive our further equation. So as you can see on your screen, that the formula to determine number of moles, that is equal to small m by capital M. Small m is a mass of a gas having a unit kg, and capital M is a molecular weight of a gas having a unit kg per kg mole. That is whatever is a mass. For example, taking a case of oxygen gas, O2. So what is the molecular weight of oxygen gas? So atomic mass is 16. So O2 molecular mass will be 32. So we called it as 32 kg per kg mole. Similarly, for nitrogen is how much? N2. So 28, right? So 28 kg per kg mole. So we would say 28 kg is a mass of nitrogen gas for 1 kg mole. Okay, so we need to spell in this form. Now, further seeing our equation, so our target is clear. We need to now bring molecular weight in our picture. Okay, that in our equation. So we have already derived a previous equation, that is our characteristic gas equation, PV is equal to mRT. Now we need to form V is proportional to N in this equation. So what I am doing, I have multiplied and divided by capital M in our characteristic gas equation. As you can see on your screen, I have written PV is equal to small m by capital M into mR into T. Okay, so you can see M, capital M is multiplied and divided in numerator and denominator. So the final equation we can write PV is equal to N R naught T, where small m by capital M is our number of moles. So I have replaced it by small m, and M into R has been called as a new constant. Let's say that is denoted by R naught, and that R naught is called a universal gas constant. So the equation finally we have obtained is PV is equal to N R naught T, and this equation is called ideal gas equation. Now our next question comes on the spot in our mind, that why R naught is called a universal gas constant. Okay, so let's find out that why it is called universal gas constant. So as we know that at our NTP condition, that is normal temperature and pressure condition, pressure P is equal to 1.01325 into 10 raised to 5 Pascal. Volume V is equal to 22.4 meter cube. Remember, for at NTP condition, the volume is 22.4 meter cube for 1 kg mole. Okay, and temperature, as we know, that is 0 degrees Celsius at NTP. So in Kelvin, it would be equal to 273 Kelvin. Now we have obtained our ideal gas equation, that was PV is equal to N R naught T. So making R naught as a subject, the equation is going to become PV upon N T. Now we have all the values. Now the values for all the gases, either nitrogen gas, either oxygen gas, hydrogen gas, any type of a gas, this value of NTP condition is going to remain fixed. That is, P is going to remain 1 bar, volume is going to remain 22.4 meter cube, temperature is going to remain 0 degrees Celsius, that is 273 Kelvin. So we would say the value of R naught will be fixed for every type of a gas. So after substituting this value, we are going to get a value of R naught is equal to 8.3143 kilojoule per kg mole Kelvin. Okay, so this is a value of a constant, and because this is going to remain same for each and every type of a gas, this is called universal gas constant, denoted by R naught, and this value is for a 1 kg mole. Remember, also as we know that we have replaced capital M into R by R naught, that is where M is a molecular weight of a gas, capital R was characteristic gas constant, and R naught is a universal gas constant. So from this equation, we can say that characteristic gas constant depends on a molecular weight of a gas. Since we know that universal gas constant R naught is going to be fixed, that is 8.3143, so the value of capital R will be different for every type of a gas. R will be different for oxygen gas, will be different for nitrogen gas, will be different for hydrogen gas. Why? Because molecular weight for all these gases are different. For oxygen it is 32, for nitrogen it is 28. So the value of R, capital R, will be changing. Okay, now actually throughout our chapter we are going to consider air as a fluid, and in some of the topics while solving numericals, if a different gas is given, that is for example hydrogen gas is given, then in that case its molecular weight and its values will be provided. So you need to keep in mind that for air, its molecular weight capital M is equal to 28.97 kilojoule per kg mole, that is shown on your screen. So from this value of capital M, we can determine the characteristic gas constant for air by using our equation MR is equal to R naught, right? So I have found out that capital R is equal to 0.287 kilojoule per kg Kelvin. So you need to keep this in mind, the value of capital R for air. Okay, that is most of the times it will be given in the data in while solving numericals, but if it is not given, then you need to use directly the value. Okay, so now we are seeing numericals based on this topic. So let's see our first numerical. So the question is on your screen. As you can see, an air receiver of volume 5.5 meter cube contains air at a pressure of 10 bar and 42 degree Celsius. A valve is opened and some air is allowed to blow out to the atmosphere. The pressure of air in the receiver drops to 1.2 bar and 25 degrees Celsius when a valve is closed. You need to determine the mass of air which has left the receiver. So let's understand this question first. So we would say that air receiver is provided, okay, and that air receiver has a volume of 5.5 meter cube which has been mentioned. Now in that air receiver, the air is present already at a pressure of 10 bar and 42 degrees Celsius before opening the valve. Remember, before opening the valve. Now what has happened? We have opened the valve and we are allowing some air to come out from the air receiver. So it has been told that after some air gets out from a receiver and when a valve is closed, so the pressure of a air receiver, or we would say the pressure of a air inside the receiver drops to or reduces to 1.2 bar. and the temperature of that air inside the receiver becomes 25 degree Celsius after closing the valve. Remember, okay, so we need to calculate that how much air has been came out from this air receiver. So definitely there will be two cases. In case 1, we are going to consider a condition before opening the valve. That is, we are going to find out mass before opening the valve. And in second case, we are going to calculate the mass of air present in a air receiver after closing the valve. So seeing case 1 before opening the valve. Now it is an application, as we know that we need to find out mass of a gas, right? So it is an application of characteristic gas equation that we have already seen. So that is PV is equal to mRT. So in case 1, the equation will become P1V is equal to M1RT1. Since the volume is going to remain same in both the cases, as the volume of air receiver is going to remain fixed, that is 5.5 meter cube. Now before proceeding, we need to keep in mind that we need to convert the units of all the parameters in our SI system. So as you can see that pressure P1 is given in bar, that is 10 bar. So we need to convert that in Pascal. But also we need to simultaneously see that a value of capital R is given in kilojoule. Okay, so corresponding pressure we need to take in kilopascal. Why? Because we know that joule means Newton meter. So if we are taking joule, then a corresponding pressure will be in Newton per meter square, that is Pascal. And if we take kilojoule, then a corresponding pressure should be kilopascal. So on your screen, as you can see that I have written pressure P1 is 10 into 10 raised to 2 into volume V1, that is given 5.5 equals to M1, that is a mass of a gas before opening a valve, into R, that is 0.287 into 315. Okay, so making M1 as a subject, and we can determine M1 is equal to 60.837 kg. Okay, so this is the value of mass before opening the valve. Okay, now this was a total mass which was present. Now taking case 2, that is we have opened the valve, some gas, some air comes out, and then after we are closing that valve. So after closing, whatever mass is present, we need to find out that. So M2 is that mass which is present in an air receiver after closing the valve. So the equation will become P2V is equal to M2RT2. So P2 is given, that is it drops to 1.2 bar. Converting it into kilopascal, we can write it as 1.2 into 10 raised to 2 into 5.5 is equal to M2 into R, that is 0.287 into T2, which is given 298 Kelvin. So we can find out M2 is equal to 7.716 kg. So this much amount of mass, 7.7 kg mass of air, remains inside the air receiver after closing the valve. So how much air has been left from this air receiver? So it would be total mass minus the remaining mass. So total mass is M1, and how much is remaining? M2. So M1 minus M2 is equal to 53.12 kg. This much amount of air has been removed, or we would say left the air receiver. Okay friends, so I hope that you are clear with this topic of combined gas law and numerical based on this topic. In our next session, we will start with our topic of CP and CV, that is relationship between CP and CV. Till then, stay tuned and thank you all.